I will be speaking about the efficacy of two different methods that can be used to fabricate fiber optic microneedle devices, or FMDs. FMDs have previously been developed in order to allow co-infusion of light energy with fluid drug delivery through a single device. FMDs have been shown to increase the volume of dispersal in drug delivery to the brain via convection-enhanced delivery by between 60 and 80%. The previous designs utilizing a fusion splicing method resulted in low optical transmission efficiencies ranging from 30 to 50%. This low efficiency could cause unwanted heating at the splice joint, resulting in thermal degradation and further reduction in light transmission. Therefore, in this work, we propose two modified fabrication methods aimed at improving the light delivery efficiency of FMDs. The first uses a solid fiber which was placed through the bore of a standard capillary, and the second was created by modifying the fusion splicing process. The solid fiber inside of capillary, or SFIC FMD, was fabricated by placing a standard optical fiber through the bore of a capillary tube with an inner diameter of 250 microns. The solid fiber was allowed to protrude by less than 1 millimeter in order to prevent light blockage by the FMD. On the other hand, fusion-spliced, or FS FMDs, were made by splicing standard optical fibers to the annular wall of a light-guiding capillary tube with an inner diameter of 150 microns using a custom splicing program. Specific changes to this program include biasing the arcing electrode by 10 microns toward the light-guiding capillary in order to allow more energy to be absorbed by the capillary, thereby allowing for a more even temperature distribution. Additionally, a two-step arc duration lasting longer than a second was implemented in order to improve the tensile strength of the splice joint. In order to test the light transmission of the two FMDs, we connected each FMD to a fiber-coupled 1064 nanometer laser. Power output was measured using an integrating sphere detector. Light transmission was averaged over a 30-second interval after the laser was allowed to stabilize for 9.5 minutes. Power measurements were taken with air, DI water, and black dye inside the bore of the FMD. Then, in order to test for potential thermal degradation of the FMDs, light transmission was measured with air through the bore of each FMD for 8 hours. After 10 minutes of light delivery, the SFIC FMD had significantly higher transmission efficiency than the fusion-spliced FMD, especially with attenuating media such as black dye through the bore of the FMD. But the fusion-spliced FMDs had an efficiency of up to 130% larger than previous spliced devices. Looking at the normalized power over 8 hours of light delivery of the SFIC FMD and the FS FMDs, along with the patch cable control, we see that the fusion-spliced FMDs had greater variation than the SFIC or the patch cable, but power delivery remained within 10% of its nominal throughout. Finally, it should be noted that the SFIC FMDs were prone to breakage at bend radii of less than 20 millimeters. This is likely caused by scribing of the capillary during the insertion of the solid fiber into the capillary and would make the FMD extremely challenging to use as a drug delivery device. While the SFIC FMDs resulted in better light transmission efficiency, it would also cause an increase in infusion pressure due to a decreased hydraulic diameter caused by placing the solid fiber through the capillary tube. Additionally, the SFIC FMDs were extremely fragile, making them impractical for clinical applications. On the other hand, the FS FMDs showed lower transmission efficiencies than the SFIC FMDs. However, they were significantly more efficient than previously reported FMDs. Additionally, they are more robust and there's little concern for splice degradation over infusions up to 8 hours. With this, the FS FMDs appear to be the superior co-delivery device, but careful analysis of the optical properties of any infusate used with the FMD will be extremely important in order to predict its efficiency in practice.